Okay, welcome. Hopefully you can hear me all at the back. Yes, I'd like to first introduce ourselves. I'm Andy, this is George. We're from Q3D Studios in the UK, a really small 3D modeling agency that works in the world of F1. So we're a little bit different. A little bit different to some of the other speakers here today that might be from the games industry. We've got a different audience, a different client. So I'll try to, explain where we come from and what our, objectives are and why and how it drives what we do. So, what are we? We work in the world of F1. I've personally been working for a top F1 team for about 20 years now. 3D modeling the world's race circuits for a driver in the loop simulator. All those years ago, the team I was working for were pretty much the first team to do a driver in the loop simulator and put the emphasis on it being an engineering tool a serious engineering tool. There was, being honest, there was a lot of engineers that didn't believe in the simulator and what it could aid the engineering. It's not a driver track learning tool, it's an engineering tool to develop the car. So, over those times, those years, it was a bit of a force to prove to every engineer in the company that it is worthwhile and what we can do. And so a lot of this was, accurate track models so that we can, develop the car and prove that this is a worthwhile tool. So back then we started with, like shown on the left, this is like CAD data, CAD drawings from your printed out massive drawings to digital drawings that we got with basic information. This is the white lines, this is the barriers, this is where the curbs are. And for about 15 years now, we've been working with Lidar survey data. So that's, I'm sure many of you have heard of it, Lidar, but this is effectively a point cloud survey system. So Lidar, light detection and ranging, which, as you can see here is a sort of quick example of what survey data may look like. So a lot of what we're going to talk about today is how we extract the information from the Lidar survey in order to create a digital twin of the circuit or of all the circuits on the F1 calendar, which we've been doing for 20 odd years.
So how does a Lidar scan work? At its core, it is a calculation of distance, very similar to how a handheld electronic measuring tape would work, where it will fire out a beam of light at a very specific wavelength, wait for it to bounce back from an object, and then measure the time that it's taken for that bounce back, and it's called time of flight. So then by timesing that by the speed of light and dividing it by 2, you can get an accurate representation of how far away something was from that sensor. The main difference between a handheld measuring tape and a Lidar scanner is that Lidar scanner's doing it thousands of times every second. It's got a spinning mirror and it's firing out the light constantly. And by recalculating it based on where the mirror was at the time of the pulse, it can work out a point cloud. So for our tracks, there's all kinds of different ways that we could be taking the Lidar data. But our one of choice is a mobile Lidar scanner. So the scanner gets attached to the back of a car, travels around the track, which is usually about 5 to 6 kilometers long, and is constantly taking these Lidar scans as it goes around, which it then combines with inertia scanners and a GPS system to recalculate the entire track in point cloud.
So what do we do this? This is, we do this for the requirements of an F1 simulator. So something I want to get across, what's different compared to what we do and maybe what a games company does. We have to literally make a digital twin of that environment. We don't have the creativity to kind of go, this looks a bit boring, let's add this detail, let's make this a bit more jazzy, let's put more into it. We literally have to make what is there in the real world. at a given time. You know, we don't have the luxury of going, well, let's have this circuit, you know, in a winter state, a summer state, or anything like that. We literally make it a single state. We know when they're going to race on these circuits, so normally in, you know, a summertime. So our job is to 100% recreate that circuit, and I can't stress it as much. When F1 drivers are picky, they pick up on details and they go, that's not quite right. You know, I've driven that curb, I can feel a bump, and there's no bump on the real circuit. We have to get that right. And yeah, Lidar scanning and Lidar point clouds gives us the ability to do that, to literally pull out every single bump, crack, you know, lump, bump detail of the surface, so that the drivers are able to replicate a lap that they do with the real world. So again, the idea of this one, and again, when they're doing a simulation, and just to try to briefly discuss what the F1 simulator is all about again, is if you have to imagine that the engineers are making a physics model, a virtual physics model of everything on the car. You know, the suspension, the aerodynamics. They will get, you know, drag coefficient details from the wind tunnel and plug that into their physics model. But I think what's fairly easy to understand is it's damn hard to make a physics model of a rubber tire. The deformation, how it rides curbs, all those details. It's really difficult, and you know, they will. You know, it's safe to say they will never make a perfect. It will never get there. It's a never-ending task. So when the drivers drive the circuit and they go, that curb doesn't feel right. Is it that the curb's not right, or is it that the tire model's not quite right? And if we can remove one of those, i.e. we can say that curb is right, that curb has that bump, we've scanned it, that bump's there, or it isn't there, and we have made a model, what we actually call a DXF model, because that's what is run, a DXF version of the model. The physics model of the tire, you know, has a load of contact patches, and it reads the polygon model underneath. We can say, no, that curb is correct. So then if it doesn't feel right, it is due to the physics model of the tire. And so it allows the engineers to develop that model a bit and make changes to make that right. So the other thing to consider is high frame rate. We run on a bespoke rendering engine, currently run on a bespoke rendering engine, because it has to have at least 120 frames per second, because the human eye can see, and these drivers are pretty damn good at seeing anything flick and change, etc. So we have to have that high frame rate performance. And due to us, unlike a game, you know, that goes out to the mass audience, you know, the budgets. We work for a single team at the moment. We roughly have to build a circuit in 8 weeks, start to finish. So that's pretty quick. If you look at some, with all the detail that we have to throw in, if you look at some circuits like a Las Vegas, we can't do that in 8 weeks. It's vast, it's huge, it's ridiculous. But some circuits, there's far less detail we can do. And we focus our attention on what's important to the driver. You know, so I'll give you a quick example. If we know that the driver's always going to drive the circuit round the right way on a high performance lap, he's never going to turn the car around and drive backwards. You know, unlike a games company or a game user, a gamer may try to go off piste and drive wherever they want, and it has to hold up on a game. For us, it doesn't matter. If you were to turn around, there might not be the back of that building because we don't see it. The driver doesn't see it, so we don't care. We don't draw it. We don't make it. We concentrate on what the driver sees and what he's focusing on, which is often quite far in the distance. So we can't do anything like LOD systems or anything like that. It's literally, we can't have any flicking. It's got to be perfect at that moment in time. Our point cloud. We have to process the point cloud, and we get the data that we get often has imperfections because it's real world. We've scanned the circuit, like you can see there on the right. There was a parked car there at some point, and of course you can't have a parked car because I think that's Las Vegas. So we can't control. Excuse me. We can't control when, is that working? Yeah. We can't control when we scan. We always scan a circuit. Sometimes it is a private circuit, you know, we can get access to it and it is a bit more of a control situation, but other times we can't. It is a public accessible location. So yeah, we have imperfections of parked cars or of people, of all this sort of data that we don't want. So we have to sometimes remove all of those. On the left, you can see it's not the best example, but it is an example of a point cloud with RGB color information. The black band down the middle is where the camera couldn't see due to the car. So we have this void. It can't get all the information that we require. So yeah, we have to take all this into consideration. We have to work with all of this data and try to remove all these imperfections. So that is a lot of what we do. A lot of the task is doing that. So we start off with, we have to, because imagine a scan of the entire circuit. We tend to have 2 to 3 billion points, which is a vast amount of points to try to process on everyday computer. So, you know, as an example, all our PCs have 128 gig of RAM to be able to just handle anything to do with this amount of data because it's just vast. So we do a few simple things like let's split the circuit up. Let's put it into 5 or 6 zones, you know, the colored zones there, just to make it manageable. And a tool, another thing that Cloud Compare does is classification. We really want to remove the ground surface, you know, and say, right, we'll work on the ground surface or the barriers or the trees, the vegetation, the buildings. We want to be able to separate these things as much as possible. So Cloud Compare allows us to either do these trained algorithms to do classification on some of this. And yeah, I could talk for ages on this, but there's some procedural algorithms that we use to do noise filtering. And basically what we're trying to do is separate it into sizable chunks that we can then work with and do more from. And then we come into Houdini. So we do a lot with Houdini, and we want to do more. There's so goddamn powerful. We're really seeing how much we can do. But as you saw earlier, there was a hole in the data due to a parked car, and we have to fill those holes. So Houdini, we've got some nice tools now to do procedurally identify holes. There could be tons, thousands of tiny little holes in the data when you're talking about such a vast size of the data set. So we fill all of these automatically and try to keep the contours of the surface, etc. To end up with, we were trying to create a meshed surface, and this is one of the jobs, the first jobs we do. So this meshed surface, again, this is, looks like that's Las Vegas again. One of the first things, is to create a surface that we can use, the underlying vertical surface. And again, due to the accuracy that we're trying to achieve, we exaggerate the scale by 20 times, just so we can see every single bump and camber and detail along the track. And of course, if you imagine the Lidar scanner can only see as far as it can see, line of sight. It can't see behind the barriers because the laser hits the barriers and the barriers in the way. We've removed the barriers because we're trying to find a ground surface. But of course, we need to understand what the ground surface is behind the barriers. Yes, the driver doesn't see behind the barriers, but we need to create a surface that we can then place barriers on, place trees on, fencing. So we tend to extend the ground surface that we can see, but consider the camber, using the normals of the surface. You can see at the bottom there, exaggerated example, we've got these 2 ribbons either side, sort of really extending that ground surface. Again, fully procedural in Houdini.
So as you can imagine, the tracks are massive and there's a lot of noise, and sometimes some things slip through the cracks, such as this beauty, which I lovingly named the unicorn horn, which we found at the exits to Imola. Your guess is as good as mine as to what it is, but nevertheless it became our white whale that we had to destroy. So I produced a tool which allows us to just take the perimeter sort of silhouette of the conform mesh and it re-topologizes the interior so that it matches that sort of form to just straight up plaster over and remove any kinds of anomalies that we find inside of the mesh. But now that we've done that, we have got a conform model which we can use to raycast all later geometries to be able to get accurate elevation and positioning for every single bit of geometry that gets made from here on. But how do we generate this geometry?
One word, splines. We love splines. We create tons of splines. And it's exactly how I've been doing it for years. Top down, 2D, I'll spline out the white lines, spline out the barriers, spline out any features like gravel traps. So we tend to do those in an optimized fashion, but yeah, 2D, Bezier, handle splines. And yeah, we've been doing that for years, and it's a manual process. That's often been me on the left. It is monotonous, it can get boring. Once you've done your 10th F1 track and you're splining it out manually, you get a little bored of it. And if you have to consider that, like that piece of racetrack there is about 15 meters wide across, and the white lines tend to be about 20 centimeters. And so in order to get that white line accurate within a centimeter, you have to zoom in quite close. You can't just like spline it out. You'll be off by quite a way if you do it that way. So you have to zoom in quite a lot to really get the accuracy that we desire. So yeah, whenever I face a task like this that gets a bit monotonous and it can take a while, I'm constantly going, can we do this quicker? Can we do this better? We must be able to improve this. And so yeah, I went to George and said, look, we must be able to improve this process.
And this was my first prototype, and it worked very badly. So don't get me wrong, the logic was sound. We decided to use a bit of data that we have already, which is the center line, which we're given for the track. And we thought if we read out and looked for changes in contrast or elevation, we would be able to find where the white lines and the barriers are, which works on paper, but in practice, given that Lidar data is taken from the real world, and the real world is a bit chaotic and noisy, the result was the same. It would have way too much noise and take far too much cleanup to actually be a viable method. It would take just as long as manually drawing it out. So we had to go back to the drawing board, and whilst we were thinking of ideas, I got inspired by this. You might have seen this around before. It's called guidance paving, and it's a wonderful bit of architecture used to help those of us with visual impairments navigate through urban environments. And they work by being a tactile surface for a cane to grab onto so that they can follow a line. And we thought if we were able to take a smaller sample of the point cloud so that we don't have as much to process at once, enhance the contrast in a way that would be able to make it tactile, and pass a cane over it with an algorithm, we could find our white lines. With that in mind, meet Tracy. This is one of our latest employees, and a very hard-working one at that, and is a custom bot that we made for specifically following paths on Lidar and tracing out white lines. So, how does Tracy work? The algorithm is a quite simple but effective one, where it samples a set radius of points, a set distance in front. The default, I think, is about 20 centimeters. And then within that radius, it will highlight the contrast of the brightest points in that area, and then read from a direction, so either left or right, which you decide, because usually when we're generating the tracks, we generate the white lines on the outside of the white line spline, so you want it to be running along the inside, as you can see there. So yeah, it reads across in a direction and finds the first point that matches its profile, and it draws a line to it, and then it repeats that thousands of times, and it has a track. And this works quite well because if you're looking at an entire track at once, there's going to be hundreds, if not millions, of points that could be considered a white line. But if you know where a white line begins and you're reading a very small amount of data in front of it, you can reasonably say that if there is a bright point there, it's probably also on a white line. So, with that in mind, how do you think that Tracy would react to a tiny little white pebble near the track? The answer? Not very well. So, It's okay, Tracy. This is actually what she's programmed to do. If she encounters a white spot, such as that little white pebble, she may take a little detour off of the track, but more often than not, she will find her way back because we coded in a little algorithm that if she stops being able to find any bright points, she'll just continue to follow the same trajectory until she hopefully finds the white line again. And then we're able to just blast away these points, and you end up with a nice, neat spline.
And so when you consider how Tracy does compared to how we would manually do it, I didn't explain earlier, but roughly it would take one of us about 2 days, 16 hours, to trace out the white lines, left edge, right edge. And via Tracy, we've managed to get that down to 1.5 hours. So huge time saving. So this sort of tool took George about a week or so to develop, including the full start with the other idea. But when you consider what we have to do is we build racetracks. You build one, you build the next one, you build the next one. Every single racetrack has white lines. There's a massive time saving overall. To have a procedural Houdini tool like this is extremely valuable to make us process these things quicker and get further. So we then looked at, instead of white lines, barriers. So Tracy's, George developed BarryBot, which essentially does a very similar thing as white lines, but it's looking at a different sample or different data set, which is the barriers. Instead of the ground surface, we're looking at another part of the Lidar data. So the barriers, which is done via classification, but it's not always perfect. The classification will have noise, it will have other buildings, vegetation that we don't want to include. And so again, BarryBot has been designed to kind of start at the barrier and trace his way along until he finds the end of the barriers. So again, similar sort of thing with Tracy. It works extremely well and it's a massive time saver.
So now that we have these splines, what do we do with them? So the first thing that we will be doing is trying to optimize the splines to get sort of a better point count, because as we mentioned earlier, optimization is massively important. We need the tracks to be running very quickly. We used to use a pipeline using standard Houdini nodes, just like measuring, attribute painting, which was quite a manual process, but it allowed us to highlight individual areas of the track and enhance their optimization, the amount of points that are on there based on how tight a curve is. But we love the versatility of Houdini, and it allowed us to make a custom Vex node called Curvature Measure Resample, which does all of those manual processes automatically, turning it from, how long roughly would it have taken to do a full one?
Yeah, again, to manually go around an entire circuit and kind of go, right, how many points do we want on the corner here because of it's this tight? Yeah, you'd spend several hours doing this around the circuit. But
yeah, this does it in about 3 milliseconds now. So big time saving there.
And used constantly.
Yes, it's used in every stage of the pipeline from here on.
So another one we use a lot is a copy to points, copy to curves. So quick example shown here is some sort of like temporary concrete barriers that are used around the circuit. So as there's cool little tricks you can do with this, not just copy it to points, but if you think about the people on the ground, when they're placing these in the real world, they're using probably a forklift truck, and they will place these down slightly skewed, slightly out, the gaps will be slightly different. All these details which make it look realistic to us, we can do. We can use attributes, we can cleverly use Houdini attributes and details to really give it that realism. It's not just in a perfect straight line. We can do some funky stuff to copy the points to make it work. And then also things like we can drive, maybe the textures, the dirt level, the different type, the randomization of the barrier to really, again, give that natural variation that is required to make it look realistic. We can use copy the points to make that happen. The power of attributes in Houdini. Another one we use a lot, sweep nodes. So, as most of you will be aware, creating the geometry is half the job. You need UVs as well. You need a good UV set. So there's no point just having geometry without any UVs or textures. So A lot of the time we'll find, sometimes we can just use a sweep node and generate the UVs, and there'll be good UVs that we require straight off the bat, but a lot of the time we'll have to generate, if you imagine a tight corner, a sweep just won't work through there, there'll be overlaps, etc. So we will generate the geometry in other methods, and then we'll probably have another path, another tree, to generate a set of geometry which has the desired UVs that we want, and then we copy them over. So copy the transfer, UV transfer or attribute transfer to make that happen. Just to try to go back and recap on a few key points, just to try to reiterate. From my perspective, I always look at the big picture. I'm just trying to keep in focus. What is the big picture? What is the outcome? What are we trying to achieve here with this tool? There's no point developing a procedural tool if that can be done manually in 10 minutes. If we've got a job and it's like, it isn't really repeated that much, and an artist can do it in half an hour, 10 minutes, whatever, and yet it will take a technical artist, a few days to develop a tool, you're not going to have any time saving. And I think from my perspective, I'm always looking to save time and do things more efficiently, maybe more consistently. And so, big picture, making sure we're not getting too deep into a tool creation to make sure it works for us and it is of benefit to the artist at the end of the day, and it will create better results. The other one, if you have to be dealing with point cloud data, is we just have to break it down, manageable data sets. It's vast, it's so much data, you can get a little bit swamped in it, and tools can take way too long to look at the entire data set. So if you can really narrow it down and go, right, let's program this tool on a small data set, then great. A bit like, Barry bot. Don't try to run Barry bot or run the entire circuit whilst you're developing it. Pick a small sample, run it along there. If it's successful, open it up to a bigger sample. Things like that to make sure it works. And the other details like, breaking it down into zones and stuff, just manageable amounts.
And then once you've extracted the data from the point cloud, you need to leverage it as much as possible. If you've got a golden spline, such as the white lines or the barrier splines, which we use to generate 90% of the track geometry, you need to find as many things that it touches that you can use as a reference to be able to generate the track. So the white lines, we use that to create center lines, we use that to create the white lines track, runoff, everything like that. You can use it to offset other things. If you can find some new way of using data you've already extracted, you are definitely winning. And another thing, if you are using Lidar and trying to create procedural methods for your environments, you should identify as many rules and consistencies between environments as you can. So we're quite fortunate because racetracks have very set rules about them. The FIA can't just suddenly make up new things, so we know that there's going to be specific barriers in specific places, such as pit exits and things like that. We know that the white lines will always be surrounding the entire track. But if you can identify set things that you can automate about the production of your environment, you're definitely going to be saving a lot of time between those different environments.
Last one, pretty obvious, as it says, complex problems don't always require complex solutions. Some of the problems we face due to the noise of the data set that we're working with, it is really quite complex. But if you can break that down into individual little chunks and try to understand the problem and really get it into simple, you can then solve those problems quite easily and then put them all together and you'll end up with a total solution, hopefully. So thank you. I'd like to, didn't thank at the beginning, but thanks Side Effects for inviting us to talk today. I don't know if we've got time for Q&A.
We do.
If we don't have time, but okay, sure.
Thank you very much.
Thank you. Very interesting. I was wondering, do you rescan a track that you've previously scanned, and can you kind of combine both data sets to filter out noise then?
To filter out noise? Or?
Yeah, like there's a car in your one scan, but it might not be there in the previous scan, so you can kind of combine this data and filter out stuff like that?
Sometimes we can do multiple runs, but then you just end up with twice the amount of data. And it's just like, yes, if we've got situations, Normally, if you're talking about a race circuit, that will have a time slot. You will have, you have to scan it in this time, and you normally have to drive them about 20 kph, because in order to get the density of the point cloud, you have to drive quite slow. So you can't just whip round quickly. And so you don't have the luxury of going, oh, let's go and do it again. Let's do it again. So yeah, it tends to just be a single scan.
I actually meant like maybe you scanned one 2 years ago and then like redo it for a new season or something?
Yeah, 100%. Circuits are changing all the time. It's great, it keeps us in work. They keep going, let's change this corner. I'm like, wicked, let's do it. So I can't count how many times Singapore have changed turn 10, it's brilliant. So, except we don't always get new scan data. We're told, they've changed turn 10, can you do something? And we're like, with what? Like, the FIA released drawings to us. If we don't get scan data, we'll have an FIA drawing sort of going, this is what they've done. And sometimes we have to work with that, and we have to turn it around in damn quick time, just a few days. Again, this is why we're moving more to procedural, to sort of be able to make those updates rapid. But yeah, I've done circuits multiple times because technology allows us to throw more at them.
Sometimes they just tell us that the track has changed. They don't even really tell us what. They're just like, yeah, a corner's changed.
Yeah.
Thank you.
Yeah. I don't know where.
Okay. If there are no other questions, I have one. Okay.
Oh.
We do have some.
Yeah, it's kind of related to the previous question, but example, like a track like Monaco, if they make a change, since it's a city track, you must have like only 2 weeks maybe to make it. How does that work out then, if they change it that quickly?
Yeah, Monaco, I recently did do some changes in Monaco, and they've resurfaced Monaco a lot, which is a pain. We can't turn it around literally, because and things like new circuits, there's a great example. If there's a new circuit coming on it, or they're making a change, they often will run right to the wire, and they'll finish that weeks before the Grand Prix. And so we sometimes have to just work with CAD drawings that we're supplied, but with the team, we don't just have the race, we have what's called driver prep, so the drivers will drive it before a race, several weeks before the race. Then during the race weekend, the drivers, obviously at the circuit, but they'll have support drivers that are in the sim, literally doing the same as what the drivers are at the race. And so if we don't get it ready weeks in advance, we can maybe have it ready for those drivers. And then there's also a debrief, which can happen 2-3 weeks after a race. They will come in and drive it again. And so we don't always hit the deadline, or we can get something out, but we'll have it for race prep, or we'll have it for the race weekend, or we'll have it for ready for the debrief afterwards.
So I have 2 questions. One is, do you consider the initial meshing of the point cloud to be a relatively solved problem? And 2, at 120 FPS, what is the target resolution? Do you have variable resolution? How many screens are you drawing to? Mm-hmm. And what features do you need to enable and disable in order to maintain that performance?
Okay, so first question, remind me, first question?
Meshing of the point cloud.
Consider the initial meshing of the point cloud to be a solved problem at this point.
Now we are able to mesh the ground surface of the point cloud successfully with our processor that we've been developing over the years, and then we build the geometry over the top and raycast or conform it to. So yes, we have. And with new graphics cards, we can throw a lot of polygons at these. Several years ago, we had to be super optimized and to hit the 120 frames per second. And the corner would look a little bit faceted at times and wasn't great. So, and things like trees, we couldn't throw as many trees, or we had to be much more like billboard trees, or the cross trees, etc. Now we can make them a bit more fancy as graphics cards are improved. So yes, I think we have solved that. Second question.
120 FPS.
120 FPS. Because it's a bespoke rendering engine, literally, the amount of shaders we've got is limited. So all of these things, we've got, like the number of textures, our texture sizes and all these. And really, we've got very simple shaders in some of them. We can do modulate between 2 different shaders or blend between a few different shaders, but we don't have shaders that allow us to do vertex colors or fancy displacement on things like that, because it's just not possible to hit the frame rate that we require. So I guess games, can make things look really pretty and make them look amazing, we have to hit the 120 frame rates first, and then we can sort of make it look as good as we can.
At what resolution though? Like 4K?
No, because it's a projected screen. Projectors can't do. So the current simulator system is made up of 8 or 9, and it's a full 300-degree screen, large, as tall as these pillars, sort of thing, large format. But yeah, it's projectors. So I think it is 1900 by 1200, and each projector sort of like there's 9 blended together, and we have a single IG image generator per projector. So and that each one has to, and then a host that talks to all of them.
Yeah, so each has their own graphics card.
Each PC, each screen has its own PC, with a 3090 or something in it.
But it's very interesting because as graphics card technologies have progressed, going back to some of our older tracks, they're running at like 500 frames a second because we optimized them for that sort of quality of technology at the time. So now they are way out of proportion, optimization-wise.
One of the things, a little bit of a teaser of what we're working on, is, as I said, it's a bespoke rendering engine, but we've got a demo, a UE5 demo working on at the moment, so we're looking to move over. Once we can hit that frame rate, which is effectively the main bottleneck at the moment with UE5, which we can consistently do, then we'll probably be able to move over to a UE5 nice, because then we'll be able to add a few more shaders and get it looking a bit more fancy. And there's other benefits as well, which I won't touch on, but yeah. Was there anything else? Any other questions? Or
I'm curious myself. Would there be benefit to switching to rendering technique that does point clouds directly, like Gaussian splatting, that you don't have to do the meshing, you don't have to do your UVs, you just render the...
We have been looking a lot at that, haven't we?
Yeah. With the real-time, I don't have a huge amount of knowledge. I know the Gaussian splatting, etc., and it was interesting with the real-time sort of guys that I work with, or that Side Effects organised, and we chat. A chap Freak gave us a talk about it, and it is a really interesting technology, and it's something to keep an eye on. But there's frame rate. There's nowhere near it can't hit anything like the frame rate that we require. And the fidelity that we require, I don't think at this time. It's something to consider, but it's not something I don't think we'll be using for a few years yet.
Yeah.
Thank you.
Yeah, we do. Yeah, the physics simulator, there is a separate, we have a visuals and a physics that run 2 slightly different models, but they're perfectly aligned.
It's also just wouldn't be able to handle the 2 billion points at the moment, I don't think. We'd still have to optimize it quite a lot, I would imagine.
Yeah.
But maybe one day. That would be very exciting.
Yeah, it's something we're keeping an eye on, but I think frame rate's not feasible at the moment.
Okay, thank you very much.
Thank you very much, everyone.
Thank you.